So that brings us to the end of the section on power basics. I'm just going to go through and summarize what we've learnt. So we've learnt that energy is the potential for a system to do work, and we use units like joules, kilojoules, megajoules, or in the power industry, watt-hours, kilowatt-hours, and megawatt-hours. Work is the transfer of energy, and the rate at which work is done is known as power, which we use for units watts, megawatts, kilowatts, and so on. Active power is the power that results in a net transfer of energy. This is the power where work is done, and this is the power that we as consumers pay for. In a circuit, this is the power where the current and voltage are in phase, and we use units like watts, kilowatts, and megawatts to describe active power. Reactive power, however, does not do work, and this occurs when the inductance and capacitance is present in our circuit, or in other words, the voltage and current are out of phase, and it has a special unit, the var. We use vars, kilovars, and megavars to describe reactive power. Apparent power is simply the vector sum of the active and reactive power in a system, and it has units volt-amps, kilovolt-amps, or megavolt-amps. The power factor is the ratio between the active and apparent power. In more technical terms, it's cosine of the angle between these two vector components. Inverters can consume and provide reactive power for reactive power compensation, as can capacitor banks in the examples we provided earlier. Many systems present a large inrush current when starting or changing state, and this causes a surge in the current that's demanded from the load. This can be mitigated through slew rate control, as well as appropriately sizing our protection circuits. Non-linear circuits such as AC to DC converters as well as transformers can generate harmonics on the grid that create challenges for how other components will respond to these systems. And that brings us to the end of the Power Basics section of this talk. Thank you for watching.